Hi everyone, I'm Daniele Rigon from the Department of Industrial Engineering at the University of Padua. The work that I'm going to present to you is titled Static and Fatigue Behavior of 3D Printed Virgin and Recycled Short Glass Fiber Reinforced and Mineral-Filled Polypropylene. The work is a part of a research project that we have in collaboration with Electrolux. The other co-authors of the work are Filippo Florian, a master student of the University of Padua, engineer Giovanni Ardengo, and Dr. Fiorella Trivellin from Electrolux, and Professor Giovanni Meneghetti from the University of Padua, which is also the scientific director of the project. The main purpose of the research project is to improve the circular economy of plastics in the white goods industries. One way is to use, of course, recycled plastics or compound, and combining the additive manufacturing process to produce components optimized by means of topology optimization, you can minimize the mass and so the usage of the plastics. So the main goal of the project is to study the structural durability of a recycled compound in order to substitute some components with new ones produced by additive manufacturing and optimized by means of topology optimization. The material under investigation is a recycled polypropylene filled with a mineral and reinforced by short glass fibers. Talking about the present work, the focus is to characterize the static properties and the fatigue behavior of these composites produced by additive manufacturing. The outline of this work are the following. So I introduce the additive manufacturing technology that we use for producing the specimen to be tested in this work. I describe the material, process parameters, specimen geometries and methods. I present you the analysis of the fiber length and the fiber orientation carried out by means of optical methods and computed tomography respectively. And then I present you the tensile, the fatigue test results, and the damage analysis. Let's have a look at the additive manufacturing technology that we use in this work. The commercial name of the 3D printing process is pellet additive manufacturing. Basically, it's a fused deposition modeling where instead of using a continuous filament as a raw material, the printer is supplied by pellets that are cheaper than the spool of filaments commonly used for FDM process. The printer is a Pollen Series P, that is an open additive manufacturing system with a wide selection of printing parameters, and it's equipped by 4 extruders that allow to print multi-material objects. With this pump system, a wide range of thermoplastics certified by Pollen can be processed, starting from standard to high-performance thermoplastics, as you can see on the left of this slide. The machine is shown on the right. As you can see, the extruder is fixed on the top of the system, while the base plate is moved and controlled by 3 mechanical arms mounted on 2 sliders on rails, and their movement are driven by belts powered by step motor located in the base. The cooperative movement of the arms allow the plate to move freely in 3 dimensions according to the X, Y, Z coordinates determined by the software. On the bottom, you can appreciate how the printer works from a camera mounted on the base plate. So, the raw material provided as a pellet differ only on the polymer matrix. In the first material, the matrix is virgin, while in the second one is 100% recycled. For comparison purposes, we compare the static and fatigue test result obtained from PAM with ones obtained on specimens produced by injection molding. This slide summarizes the main process parameters adopted for producing the specimen to be tested. It worth underlining that the PAM parameters have been optimized for reaching a compromise between high printing speed and satisfying mechanical properties. Therefore, another set of parameters could lead to even better mechanical performance than those I'm going to present you in the next slides. The PAM specimens were produced according to this geometry for the tensile test and fatigue test with load ratios equal to 0, while for fully reversed fatigue test the gauge length was reduced to avoid buckling under compression loads. The specimens were produced in a flat orientation with the three infill patterns indicated by the angle theta that represented the angle between the load and the deposition direction. So F0 means filaments oriented at 0 degrees with respect to the load applied, F90 oriented to 90 degrees, while for F minus plus 45 degrees means that from one layer to another layer the deposition angle changes from plus 45 and minus 45 degrees. The printing strategies consist in depositing first one contour part and then fill the layer with the relevant infill patterns. Finally, the infill density parameter was chosen to be constant and equal to 100% for all specimens. For the IM specimen, net shipped type 1 specimen from ASTM D638 part 4 were produced and used to tensile test, while for the fatigue test, smaller specimens were machined from the previous one to avoid buckling during the compression load in the fatigue test with load ratio equal to 1. The experimental setup consisted in electromechanical testing machine, StepLab EA05, with a test center StepLab controller. The static load capacity of this machine is plus minus 5 kilonewtons, and the dynamic load capacity is limited to plus minus 3.5 kilonewtons. The tensile tests were carried out in displacement control mode and with a displacement rate equal to 25 mm per second. Recording the strain, the engineering strain, we use AMTS extensometer with a gauge length equals to 10 millimeters, and the constant amplitude fatigue test were carried out with two load ratios, -1 and 0.5. The load frequencies applied ranged from 2 to 24 Hz, and it was limited by the maximum temperature of the material reached during the fatigue test. It was 30 Celsius degrees, and the temperature measurements were carried out at frequencies of 0.1 Hz by means of copper constant and thermocouples by using a data logger agent. Before testing, one sample from one specimen per series was burned off in a muffled furnace at temperature of 550 Celsius degrees for 3 hours. The fibers were cleaned by using hydrochloric acid, then filtered and dried to remove the residuals of the mineral filler. Several images were digitally acquired using an optical microscope to obtain a total number of fibers per each material ranging from 1000 to 1040 fibers. The lengths were measured manually by processing the image acquired by using the ImageJ software. As can be seen the distribution divided by technology in a row and by material in the columns are well fitted by a type 12 Bird probability density function, which equation is reported in the slide. The numerical and weighted means values are recorded within the graph, and as can be seen, by analyzing the same technology, the recycled matrix provides a lower mean values of the fiber length. Starting from the same process to produce the pellets of both virgin and recycled compounds, one can hypothesize that the higher fiber breakage can occur due to different rheological properties between virgin and recycled matrix, but further investigation on these are ongoing. Looking at the same material, for both materials the mean values of the fiber length are higher in specimens produced by PIM than by AEM. This could be due to the higher shear rates that occur in injection molding process that are known to be the main cause of fiber breakage. By means of computed tomography, we have also analyzed the fiber orientation only for the recycled material. From the AEM specimens, one sample taken from the gauge part of the specimen was analyzed. The color image reports the cross-section of the specimen indicated the center lines. The color bar reporting the colors related to the angle between the fibers and the z-axis or load direction is reported in the bottom right of the slides. As you can see, in the IM specimen, there is a part in the core of the specimen with the fibers oriented between 60 degrees and 90 degrees with respect to the load direction or z-axis. In the remaining part, the fibers are overall parallel to the load direction. Let's see now the F0 specimen. The sample, in this case, was taken at the end of the gauge part of the specimen in order to highlight the detrimental features caused by the automated scanning strategies proposed by the software. In fact, in this case, after having filled the layer, the extruded should interrupt the flow of the material and move in the narrow region. But actually, a trickle of material remains and generates these strips with fibers oriented at 90 degrees with respect to the load applied. As can be seen in the XY section, these path changes occur in the same position in each layer, generating a weak point of the specimen. It was our intent to not modify the G-code to avoid this problem, since these anomalies could occur even in a more complex component when the scan strategies is automatically generated. If instead we're looking at the cross-section on the gauge part of the specimens, see the section red, it presents only fibers oriented between 0 and 30 degrees. This proves that the fibers are well aligned along the direction of deposition. The following analyses were carried out on the F19 specimens, where it can be clearly seen that the fibers are oriented at 90 degrees except, of course, in the wall part of the layer. And finally, the same features can be observed in the F45 specimen, where the fibers are oriented between 30 and 60 degrees. Let's now have a look at the tensile test results. The first graph, letter A, showed the engineering stress strain curve of the virgin and recycled specimen produced by injection molding. As you can see, the recycled matrix degrades both the Young modulus, the tensile strength, and the elongation at break of these specimens. Figure B reports the comparison between the virgin material produced by injection molding and pellet additive manufacturing. It is interesting to note that F0 degree specimen has the same elastic properties of the IM material, since the curves are well overlapped at the beginning. However, the premature failure in this case occurred due to the defect formed by the scanning path that had been shown in the previous slide. On the contrary, the infill pattern F45 and F19 show a lower elastic modulus and tensile strength, but comparable elongation at break with respect to the injection molding ones. The same trend just discussed can be observed in figure C, where in this case F0 degree stress strain curves are not overlapped as well as the previous ones, and the F45 has higher mechanical property than the F90 degree. Figure D, E, and F reports the comparison between the virgin and recycled materials for each infill pattern, highlighting the same behavior observed for the injection molding ones in figure A. Finally, on the right of the bar chart, the bar chart has been reported with the mean values of each static properties for each test series. Let's have a look now to the damage mechanisms after tensile tests. The injection molded virgin and recycled specimens exhibited similar microscopic failure modes as reported in the first column of the table, with the fracture surfaces almost perpendicular to the loading direction. This result is consistent with the literature regarding the short fiber reinforced polymer composites with mold field direction parallel to the specimen axis. Analyzing the fracture surfaces, one can see diffuse fiber pull-out, broken fibers, and diffuse fiber matrix bonding, which probably induce cracks in the recycled matrix. In the case of virgin F0 and recycled F0 specimens, the failures initiated at the start point of the fillet due to the presence of voids at the interface between the wall and the infill, and by the presence of the defect generated by the peculiar infill strategies already presented that cause a weak point in the material. The fracture then propagates in a zigzag appearance, more pronounced for virgin than the recycled specimens, due to the interlayered delamination and the bonding of adjacent filaments. In the case of virgin F19 and recycled F19 samples, the fracture surfaces were planar, normal to the loading direction, and located at the interface between adjacent filament. Finally, microscopic fractures, almost perpendicular to the loading direction, were observed in the case of virgin F45 and recycled 45 specimens, as shown in the last column. Let's now have a look at the fatigue test results on injection molded virgin and recycled specimen. On the left, you can see the SN curve in the double log scales, reporting the results of the fatigue test with load ratios equal to -1, while in the left, the result relevant to the test with the load ratio equal to 0. The sigma A is the stress amplitude of the cyclic load, and in the figure, the black points are related to the virgin compounds, while the red ones refers to the recycled specimens. In the high cycle fatigue regime, precisely at 2 million cycles, the fatigue strength of the recycled injection molded specimens is 31% lower than that one of the virgin material for load ratios equal to -1, while for R equal to 0, the reduction is only the 14%. Furthermore, the difference in terms of inverse slope K of the fatigue curve, statistically evaluated on data, suggests different damaging mechanisms between low and high cycle fatigue regimes for R equal to -1, though this is not observed for R equals to 0. These slides show the fatigue test results of recycled materials produced by additive manufacturing for R equal to -1 on the left and R equal to 0 on the right. More precisely, in this figure, the black point refers to the F specimens, the red ones to the F45, and the blue ones are referred to the F19 AM specimen. For comparison purposes, the previously seen fatigue curve for recycled EM specimen is reported for both load ratios in green. The same anisotropy seen in the result on static test can be observed in the fatigue curves of additive manufacturing specimen, where the best fatigue performance are obtained on F0 specimen, while the lowest fatigue strength is obtained on F19 specimen. Furthermore, all the PAM fatigue strengths are lower than the results obtained in injection molding specimen. Looking to the macroscopic damage mechanisms, as reported in the first column of the table, injection molded virgin recycled specimen exhibit the same macroscopic failure modes observed in static failure, with fracture surfaces almost perpendicular to the load direction. In the case of recycled F0 specimen, the failures initiated at the start point of the fillet due to the presence of defect generated by previously illustrated peculiar infill strategies, and then propagated in a zigzag appearance. In the case of recycled F90 samples, the fracture surface is planar, normal to the loading direction, located at the interface between adjacent filaments. Finally, the macroscopic fracture surfaces is almost perpendicular to the load direction observed in static failures, as shown in the last column. We have planned to analyze the damage mechanism by observing these fracture surfaces at the scanning electron microscopy. For comparing the observation with the static failure modes previously commented. Finally, the conclusions are reported in the next two slides.